Yes. So today we are jumping into kind of the closing of chapter 13. If we have time, I'm going to try to do a bit more on the physical applications of this. These are going to get treatment in your physics courses for those of you going on into physics and engineering and such. And they'll do a much better job, to be quite honest, right? I'm a pure mathematician, not a physicist. But it's fun to see the kind of underpinnings of these things, as well as to maybe drive at some proofs when it's called for. But today, giving you some of the kind of fundamental ideas that are going to drive the rest of the calculus that we're going to build on multivariable functions. We're going to wrap up the idea of tangent lines and tangent vectors, as well as unit tangent, which is a big idea. I'll point to something called the TNB or the Frenet frames, which are, again, something living in kind of the physics world, but nice to know, nice to have in our back pocket. And then two big notions of arc length and curvature. Okay, how curvy something is, and how do we figure out how long a stretch of curve is for a space curve based on just being given the formula. Right? We're going to use calculus, and if you recall that particular unit from Calc 2, that will help. But I'll give you the formula to refresh us when we get there. The reason that we want to do this, I'll give a quick overview and then we'll jump in. The reason that we want to know about arc length and curvature and be oriented, and I mean that in the sense of like making sense of these structures, is that if we're going to integrate, differentiate on these curves, on let's say a particle moving through space, we want to be able to talk about, how much its path is twisting. Um, we want to talk about how far it's gone per unit length or per unit time. And if we parameterize a path differently, I think we saw this a couple sessions ago. You can parameterize a circle in a bunch of different ways, but based on how you parameterize it, first, moving from t from 0 to 1, you could go all the way around. You could go around 14 times, right? Or you could only make an eighth of a turn. So what we're going to do is dodge that whole problem of parametrizing with respect to like quote unquote time and reparameterize curves with respect to the arc length. How can we write an expression for this curve that's just based on how far you are along the arc, if that makes sense. Okay. So then when we're talking about things like the rate of change with respect to the curve, now we're talking about the distance on the curve instead of some parameter t, which may or may not hold any value for us. And then curvature, again, a big idea tied to arc length, and it will tell us more and more about these relationships. And curvature, again, is really just the failure of a curve to be linear. Okay, so how far off from being linear are you? This is going to be like an index that measures that for curves. Okay. So with all that being said, those are the kind of big ideas. We're going to dive in right now to tangent lines and vectors and kind of tie off section 13.2. We'll have a few more worked examples today, too, and a little bit less lecturing. So, some things to note here. For a space curve, r of t, a vector function with some parameter t, we call r prime, which we talked about last time, the tangent vector. And how do we define r prime of t? Well, if r of t is some, f of t, g of t, h of t, its components are defined by some real valued functions. Then remember, this is given by each of the derivatives. It gives us the direction of the rate of change of r, as well as the magnitude, right? How much it's changing by. And that's at an instantaneous level. That's the power of calculus. There are, and we'll see today, reasons why we actually would like to preserve the direction of the tangent vector, but strip away the magnitude. Maybe we don't care about how fast it's changing with respect to t, but we just want to know what direction it's turning in each point. All right, what's the direction of the tangent vector at each point? And so what we do, let me ask you, what do you think we would do to preserve the direction but not the magnitude of the tangent vector?
Just divide it by its magnitude?
Divide it by its magnitude, yes, thus creating a what type of vector?
Unit.
Yep, unit vector, that's right. Unit vector has magnitude 1, so we can scale it to do whatever we want it to do. It really just preserves the direction of the curve. So we call big T of t the unit tangent vector. And we define it to be the tangent vector divided by its magnitude. You'll also sometimes see this double absolute value sign for the magnitude. It means the same thing. Okay, so I want to put it there just so we're seeing some of the variants of notation and not getting confused about that. So it's the unit tangent vector. It has magnitude 1. Length 1. Preserves only direction of tangent vector. Okay. Let's look at an example that highlights the relationship between these things. So let's say if we're given some vector function, and it's t squared I hat plus 2 sine t j hat plus 2 cos t k hat. Find the tangent vector function and the unit tangent vector. So before we do that, quickly looking at the formula for the space curve and thinking about the shape it should take. Again, eventually you get to higher dimensional stuff. This doesn't matter. But it's nice to have whatever orientation you can, to have whatever sense making you can. What does this thing roughly look like to you? Or what's it doing?
It looks a lot like the trig identity, sine squared plus cosine squared equals 1.
Nice. So it has, it has a sine and a cosine, so we're feeling like it's got some relationships to the Pythagorean identity, something dealing with circles, right? This is good. And I know you guys are, this is kind of your first time around with these types of functions. But remember, this is giving me my x coordinates, my y coordinates, and my z coordinates. You think this is tracing out this relationship. My y and z are related by this 2 sine t plus 2 cos t, right? My y coordinates are given by sine. My z coordinates are given by cosine. So I'm thinking like in the YZ plane, I've got kind of these circular cross sections going on, right? And then my x coordinate is being given by t squared. So as time goes on, right, starting at t equals 0, It's where? It's out here on the z-axis up at 2. And it's living on this cylinder of radius 2. And it's going to trace out alongside. This is a terrible picture, but it's going to do something like this. It's a helix that wraps around the cylinder of radius 2 that's on the that's sticking out from the YZ plane, right? It lives on the x-axis. Does that make sense? With the way I look at this, I'm seeing, all right, this is generating some swirling from that plane, and then this is stretching out my x, right, in the t-squared direction. Does that make sense? So it's just kind of an intuitive way to think about this curve. So maybe that will also inform what we see from the tangent vector. So r prime of t. What's going on with my chalk here? R prime of t is really the derivative of each of these real valued functions for the components, right? So it's going to be 2t I hat plus 2 cos t j hat minus 2 sine t k hat. And again, if I blast through these two quickly, maybe we're rusty on differentiation rules. A, make sure you refresh those, and B, you can come back and, watch the video again later. But try to keep up and make sense as we're going through. So r prime is given by this function. This dictates the tangent vector at each point. So here it's doing something like this. It's pointing the direction in which the curve is heading, right, at each t value. And it also has that magnitude on it of how much. So at some points, if it's not, bending a lot, it's probably going to be a lower magnitude. This is the tangent vector. And so then big T, or the unit tangent vector, is r prime over its own magnitude. So that's really, right, we can think of this as 1 over the magnitude times, with conventional multiplication, scalar multiplication. And so we're going to need what that magnitude is. So, right, it's the length of the vector at time t. So that's 4t squared plus 4 cos squared t plus 4 sine squared t. And then Alex's theorem is going to come in here and help us simplify this a bit, right? So get 4t squared plus 4 under the radical, right? Factor out the 4, and the cos squared plus sine squared gets you 1. I'm going to take it one step further, factor out that 4 from the square root, and just get a 2 radical t squared plus 1. In general, and I mean in general, not every time, to simplify as best you can, probably the right call. Okay, because a lot of our calculations get a little laborious, so it's best to reduce things as much as you can. So here's this magnitude. So this is really 1 over 2 radical t squared plus 1, all times 2ti plus 2 cos tj minus 2 sine tk. This becomes what? T over. Yeah. So we had our tangent vector, and this is our unit tangent vector. You know, it's kind of impressive that given a space curves formula, the trajectory of some particle at time t, that we're able to, at each moment in time, find out what direction it's pointing in, right? Which direction it's heading. It's instantaneous rate of change of the direction, right? And not even the magnitude of that R of t function. So that's what that means. It preserves the direction, and it's the rate of change, right, of the direction. So did I say it's the rate of change of the? It's not the rate of change of the direction. It is the direction of the tangent. Okay. That's a second order thing, is what I just uttered there. Okay. So one quick follow-up to this then is, let's find the tangent line to the above R of t at t equals pi over 3. Anybody refresh me on how we would do such a thing? Well, what do you need for a line?
Couple points? 2 points. Yeah.
2 points would be great, or at least 1 point and
Some sort of slope or directionality in space.
right, yeah. Slope kind of fuzzily gets mapped to direction in R3, right? So we need a point in the direction, or just 2 points, and then we can get the direction, right? So an L, a function L, what are the ways that we can represent linear functions?
Through a vector equation or a parametric equation.
Right. We could do vector form, we could do symmetric equations, right? Or we could do parametric. So let's look at a vector equation for this line. So it's going to be what? R naught plus TV. What are these vectors here again? R naught is just the point on the line, right? The position vector of any point that's on the line. And then V, so this is, position vector of O to some P naught. And then here, this is a vector that's parallel to the line. So here we're talking about the tangent line to this curve. So what should we use for that vector V?
The unit tangent vector that we just calculated.
For sure. We could even just use the tangent vector itself, right? We don't need to necessarily use the unit tangent vector. Reason is t is going to scale, unless we're given some restriction, right? T is going to scale that vector anyway. So it's just, we just are really looking for that direction. So you could use either, is what I'm saying. It's not necessary. So OP naught, well, what's this point on the line? We actually need to be careful about that, right? We can't just grab any old point. This is going to be at the point of tangency, right? What are we doing? In general, that's not what I drew. In general, if I have this as my curve, here at this point of tangency, I'm looking for the line that is tangent to the curve. So it's going to be parallel sitting on top of r prime of t at that point. And this point right here is at this moment, right? This is the moment at which we are tangent to the curve. It's the moment we care about. So this is really, we're looking for r of pi over 3. That will give us that point in space. All right, it's going to give us what? F of pi over 3, g of pi over 3, h of pi over 3 as the position. So we're pretty much there. Just a matter of plugging this stuff in and going for it. So find r of pi over 3. That's what? T squared, pi squared over 9. And we'll get 2 sine pi over 3, 2 cos pi over 3. And just to simplify this a bit, right, sine of 60 degrees is radical 3 over 2. So this just becomes radical 3. Cosine of 60 degrees is 1/2. So this just becomes 1. Is it negative? No, positive. So this is the point we're at right here. And then we also need the tangent vector at that point. Right, which we know, we come back up here, this is our tangent vector, and we're really looking for this evaluated at pi over 3. That's the tangent vector at that moment in time, right? So it's what? 2 times pi over 3. We got, this is 2 cos pi over 3, negative 2 sine pi over 3. So that's this guy right here. And so then in vector form, we've got everything we need. We've got the point we've got the direction. So then this linear function of t is really r naught. So you could say pi squared over 9 radical 3, 1 plus t times 2 pi over 3, 1 negative radical 3. Or if you put it into parametric form, just to kind of refresh ourselves, we could get these guys as pi squared over 9 plus 2 pi over 3t. Y is given by radical 3 plus t, and z of t is given by, what, 1 minus radical 3t. If anybody can figure out why my pencil thinks it's tilted when it's not, I'll buy you coffee. If there's any Apple developers out there looking for a bounty. So we've got the parametric equations, vector equations, and how do we find the symmetric equations again? Great question, Mally. Thank you, class. Thought of it myself. How do we solve for symmetric equations? Well, we should do it. We just solve for t on each of these. You're implicitizing it. You're getting rid of the parameter. So what do we get? We get x minus pi squared over 9 all times, well, let's say, we'll do it like this, all over 2 pi over 3 equals y minus radical 3 all over 1 equals z minus 1 all over negative radical 3. So just solve each of those for t and then set them equal. Not too terrible. Okay. So a quick note here about some stuff that, again, if we had time, I'd expand on it, and that might happen. And I know I've said that about like 5 things already in this class, but you know, we'll see. I'm hoping for a rainy day, not another snow day though. So some stuff that would be cool to dig into, and you'll probably see in physics classes. But the idea of the tangent vector, the tangent unit vector, has some nice stuff that comes with it. So maybe we'll take a second to just visualize what's happening with the tangent vector. So, right, if I have some curve, I'll separate this from that. Some curve r of t. At a given point, tangent vector is, right, of length 1 pointing in the direction that the curve is heading. Now this is a little bit off just so you can see it. But right, it's supposed to be parallel to the curve itself. Right, it has the same direction at that instant that the curve does. So what pops up is a few other vectors. So we'll call this, all right, the unit tangent vector. Since it has length 1, all it's preserving is the direction of the space curve. So what you get as well is if you take a look at the rate of change of this curve, right, of big T of t, what are you really talking about? You're talking about the rate at which the direction is changing, right? The rate at which the direction is changing. What is that kind of related to from the physics world?
Acceleration, right?
Yeah, it's tied to acceleration. So this is telling us how much the direction, the rate at which the direction is changing. And so if we take that and what we call normalize it, meaning make its length a unit, right? 1 unit. So we divide by its own magnitude. All we're really doing here then now is we're stripping out the magnitude and saying we don't care what that is. We just care about the direction in which the direction is changing, right? And we call this the normal vector. Okay. The normal vector has some nice properties in that it is always orthogonal to the tangent. Had another note here too. Maybe not. All right, well, in any event. I'll wake up in the middle of the night and remember what it was, I'm sure. So we know that, n dot t equals 0, meaning n, t are orthogonal. And also notice that there is a third vector that co-travels with these two. If we took the tangent vector and crossed it with the normal, we get what we call the binormal. So I'll just put this kind of for future study. This won't be on the test. I know it's always in the back of our minds. I hate saying it, but it's not going to be on the test. So the binormal vector, and if I can, I will put up on here yeah. I was a little crazy, but we'll show it to you. All right, can you guys see that okay? All right, so what you're seeing here, if I can get myself set up here. So this is the curve we were just working on. Oh my gosh, I'm dizzy. Okay, this is the curve we were working on. It's the t squared plus 2 sine t j plus 2 cos tk. You see that position vector in dark blue here. If you have trouble seeing colors, I apologize. Trust me that this thing's just hard to see, period. But the blue vector is the position vector of the point. And what you see in purple or pink here, can you guys see my cursor? In purple or pink here is the tangent vector along the curve. And here this is the unit tangent vector, and this big one here is just the, I believe that's the full tangent vector. You'll also see these N and B, and you'll see how they are orthogonal to each other. The normal vector is showing, again, with length 1, the direction that it's turning inward to. It's kind of curling towards, let's say. And B, the binormal, is the vector that's perpendicular to the plane that T and N form. All right, I'm kind of cocking my head so you can see there's this box drawn in there. But I'll put this in the notes too so you guys can play with it. And again, as you scoot it around, you'll see that these vectors kind of co-travel, and they call this the TNB frame, or the Frenet-Serret frame. I know that I'm mispronouncing those French names. Okay, so kind of just a lot of information is in every point along a space curve as long as we have it parametrized. And so the next kind of section is, how do we keep all that good stuff and strip away some of the problems that come with parametrizing a curve in a non-unique way, right? And we can do it based on the arc length instead of some unit time that we just kind of came up with. All right, so this is cool stuff. Again, not on the test, but just to know that there's a lot more depth here, probably on all of the topics that we cover than we have time for. So questions on tangent lines, tangent vectors, unit tangent vector. Not too bad, right? Not too bad. Okay. So next up, again, we're looking at arc length and curvature. How can we generate a perspective on which to integrate and differentiate? That's just based on the curve itself and not the parametrization. So arc length. So let's recall how we did this from Calc 2. Anybody remember that? A length segment. I had some curve. Let's say I had it parametrized as x of t, y of t. And I wanted to know from here to here, right, how long have I actually traversed? And we'll call this f. Anybody recall how to do that? So it's and for those of you in the seminar class, right, this is a curved versus a straight problem, right? Trying to calculate something, a distance on a curve, you need to use calculus, right? You can't just do this with algebra. So what you got to do is cut it up into a billion pieces and then add it up again, right? This is how we calculate how far we've traveled with our pedometers, etc. And so to chop something up and to add it all up, is that differentiation or integration? Yeah, see some of us mouthing integration. Yeah, integration, adding it all up, right? So, and what are we really adding up? Well, if we were able to zoom in here, we'd see this curve. What we do is take these, little bitty pieces and find out how far did we go up over, how far did we go over, right? And this would give us this length, and then we'd sum all those pieces up. So the idea was that the length on A to B was given by the integral from A to B of the square root of let me do it this way. X prime of t squared plus y prime of t squared all dt. Another way to think about it, probably a better way to write it, honestly. The derivative of x with respect to t squared plus derivative of y with respect to t squared dt. Okay, because if you think about each of these things, they're going to be best approximated by the derivative, right? The instantaneous rate of change. So you're summing up those instantaneous bits and getting the total length as you go. So that's why this looks just like the distance formula, right? So that's how to find how far you've walked along a 2D path. How do you think this is going to look in R3?
Just going to add a third term under the square root.
That's right. You add z. That's all of Calc 3. Just add z and you're done. Welcome. Welcome to higher level math. Just add z. No, but in some cases it is that simple. And here, yeah, you're adding that third dimension to the distance. So you get, right, that length. And I'm going to be actually more careful about how I write this. But from A to B, some interval, and again, this is from t equals A to t equals B because this thing is parametrized. Square root of how the x is nudging squared plus how the y is nudging squared plus how the z is nudging squared. Another way to write this, integral of the magnitude of the vector function, of the derivative of the vector function, so the magnitude of the tangent function with respect to t. Okay. This is at least not dependent on the coordinate system that we're in, right? Eventually we're going to change coordinate systems, and this is not going to help us. But this is the generalized idea. Magnitude of the tangent vector summed up from t equals A to t equals B. Okay, so that's arc length in R3. And again, that's on a space curve. All right, so let's do an example. So determine the distance traveled by a particle whose position is given by the vector function t cubed over 3 4t, 2t cubed on 0 to 2 seconds. So there's kind of two schools of thought on how to do this, right? Distance traveled is an analog for the arc length along the curve, right? So we could either find this, which is the magnitude of the tangent vector, or we could go about it kind of more piecewise and look at it this way. Doesn't quite matter. They're both the same thing, right? This is in here. This is the length of that tangent vector at each point t. So we will go ahead and do, we'll do this piece here. So finding, dx dt, dy dt, dz dt. Well, the derivative of t cubed over 3 is just t squared. Derivative of 4t is just 4. Derivative of 2t cubed is 6t squared. So then the distance traveled is going to be that length from t equals 0 to t equals 2. The square root of t squared squared plus 4 squared plus 6t squared squared. Plus what? Plus 16. 36t to the fourth. I think something backwards here. Oh, this isn't going to work out. Small edit. This guy up here is supposed to be a squared 2t. And it's supposed to be a radical 2t squared. Wow. Need to call the eye doctor, but that's for me to do. All you guys need to worry about is to adjust this so that things work out. One thing I've learned about this course is carrying through little issues does not pan out. It can totally work out up through Calc 2. You can kind of just hustle it through. Not the case in Calc 3. So we're actually gonna go back and fix that. So that means dz dt should be 2 radical 2t. That means this guy is 2 radical 2t squared. Which makes you what? 4 times 2, 8t squared. Which makes this thing factorable, which is what we want, right? Trust me. So, and if you need time changing that up. In my master's program, when the math orientation people were like kind of showing us around what you're going to need and stuff, they took us to the bookstore to buy the art student erasers before the art students got there, because we need them because we make so many mistakes all the time. You need like the big 3-inch block rubber eraser. So you'll get used to it. But we've got this thing, and why that's nice is because it's factorable, right? And since the t values are positive, we don't really have to mess with worrying about negative values. So we're going to take that, and that's what? T squared plus 4 squared. And so if we integrate that from 0 to 2, we'll get 1/3 t cubed plus 4t between 2 and 0, which should leave us with what, 8 thirds plus 8, 32 thirds. Again, what is this? It's units traveled by the particle, right? So whatever the distance was, which I didn't give to you, it's units of arc length. So how far it really traveled along the curve instead of just from A to B. Does that make sense? Is this thing on? Hello? Signs of life? Excellent. All right. Good. So not too bad. Really, it's arc length from Calc 2. We add in the third dimension because distance is treated the same in the Cartesian coordinate system. So why that's really cool is because we can take that a step further. We can now define a function, right? Because since I can do this for any t values I want, as long as the thing is differentiable, right? I can do this at any point t. And so now what we can do is define a function. We use this little s of t as the integral from 0 to t. And I'm going to use a dummy variable here, r prime of u du, right? Because this doesn't really matter. We're really going from 0 to t, summing up those bits of length, which again, if we translate it to our other formula, it's dx du squared plus dy du squared plus dz du squared, all du. You see the difference between the two formulas here?
Yeah, you just get to make your bounds of integration cleaner, right?
Yeah, we get to choose the bounds of integration. And really, this is at any point a to t. It shouldn't just be 0 down here. I would double check how it's defined. I don't think it's defined with 0. Maybe it is. Maybe it doesn't end up mattering, but we'll keep it at 0 for now. So anyway, yeah, it changes up the game a little bit. Before, what we were able to do is do it as like a one-shot process, right? Here, we're able to make it a function of time. So how far along the curve, right? How far are we letting time go so that we can grab how far we've traveled and add up that distance. Okay, so it makes it a function of time. So now we have this separate function of the arc length, which is like tethered to our r of t, the pencil tip tracing this particle's path out. Okay, so the idea is that you can let both functions go, right? R of t and s of t. R of t will tell you the blank, and s of t will tell you the blank at time t. Just to kind of make sure we're all on the same page. R of t will tell you what at time t?
Your position, right?
Yeah, the position. and S of t will give you the arc length at time t, or you can really think this has been traveled between between 0 and t. So starting at t equals 0 up to time t, how far you've gone. Okay, awesome. So let's practice that idea. Find an arc length function for, again, some position vector function. T squared 2t cubed 1 minus t cubed. Hey, Mally, you're keeping these vector functions pretty simple. Yeah, that's because I don't want to get bogged down in crazy radical calculations mid-class. That is, important to practice with, but it's much more important to highlight the ideas than get into the nitty-gritty. That's for problem sets, right? That's for the fun stuff. So, but no, honestly, if we did those, we just wouldn't get through the material. So we try to keep it simple. So here, how are we going to do this? S of t. Also, you'll notice I just backtracked that notation, right? I put a vector sign on it and then took it back. Why is that?
It's telling you a length.
It's just telling you a length, which is not a vector, right? That's a scalar, right?
Yeah.
So we should make this note that this is a scalar function or a real valued function. And again, that becomes, it's just important to know the difference. It's important to know the difference. So yeah, S of t is a scalar function. It's the integral from 0 to t of the sky. And so it can be helpful to first find r prime. Well, thank God we kept it easy, Mally, because now we can just take these derivatives. Let me make sure I didn't make a typo there too. Looks good. All right. So that is the what vector function? Rhymes with schmangent. Tangent vector. Tangent vector. This is the tangent vector function. We want the magnitude. I never said the jokes would be good, by the way, guys. That was not part of the deal, okay, for the class. So magnitude is going to be 4t squared plus 36t to the fourth plus 9t to the fourth. Right? I don't like creating too many shortcuts, but right, we compute magnitudes a lot, and in the Cartesian coordinate system, it's really square the components and add them up, right? So I'm kind of just fast forwarding through these a little bit. So 4t squared plus what? 45t to the fourth? And we are keeping t greater than or equal to 0, so I'm going to go ahead and pull a factor of t squared out. So we've got that. All right, so we've got this piece, so that's going to go here. So then S of t is really the integral from 0 to t. Of this, it's u. We're using our dummy variable, 4 plus 45 u squared du. So how do I deal with that? Can I get this to an explicit function of time without using an integral, or get it to closed form, as we say in the biz? Can we integrate that?
You can fundamental theorem it, like.
Yep. Use the fundamental theorem, but integrating this function that we have, how do we do that? Well, we do a substitution,
Yeah.
right? So then we've got what, that dw is going to be what, 90u du. And so we've got w to the 1/2 here. We've got almost the dw, so we need to take this dw. Let me do it like this. So now we can make our full substitution, right? So we get w to the 1/2. 1 over 90 comes out front. dw, which becomes 1 over 90 right? Yeah. No longer on par with my notes. I'm wondering if the notes are wrong or if I'm wrong here, but we'll figure it out. So what this becomes times 2/3 w to the 3/2 between t and 0. We're not gonna bother with the subs here for now, right? Maybe I should actually be super careful and go to indefinite for a moment, so I don't have to worry about the bounds of integration, right? Subbing those in for w. So what do we get? We get this all plus c. So 2 over 45, 3 times 45 is 135. W to the 3/2. And then if we go back to what w is in terms of u, this is just kind of some side work to help us finish off this integral. This is all between t and 0. Just finding parking wherever I can right now. And then what this becomes 1 over 135, 4 plus 45 t squared, all to the 3/2 minus And then I actually do have a non-zero value when the u is 0, and we'll get that to be 8. So what does this tell us? It's the arc length of r of t at time t. So pretty nice to be able to generate a function that tells us that based on the same parameter. Some things about that. Well, just that, this can be, since you're relying on integration, depending on how your function's parameterized, this will go from as challenging as that was, which was not too bad, to very, very challenging, right? Or sometimes even impossible, depending on how you chose your parameterization. So you could choose a new parameterization to switch up how the integral would go, or something like that, or go for approximations, right? But this is how you would do it exactly. So it's not always possible to get an explicit function for arc length. But there we could, so we did. Because life is short, Why not? So, yeah, in this next example, that's what I want to do is remove the parameterization based on t and reparameterize a curve based on the arc length, right? So tell me where I'm at based on the distance traveled instead of some parameter t. Again, why would we care about this? It might be a tougher question than I think it is. For now, you can kind of frame it under, more information is good, right? But parametrizations are not unique, right? So even just to kind of hinge it on the last thing I said, which is that depending on how you do that, doing other things or analysis with other functions can go from, tedious to impossible. To go to arc length, this is really going to be a unique representation of the curve that you have, and it's not going to depend on some other variable. It's going to be the curve is the curve in a way to really kind of simplify it. So, and when we're talking about actual physical applications or what the structure of this thing really is at its core, we'd be more interested in talking about it parameterized with respect to arc length than some t. So, anyways, I'm making too big of a point about this. So let's just work through an example quick, and I'll show you how we do that. Yeah. So let's A, find the arc length function. For RFT, and I'm going to have you guys do this. So it'll be A, and then for part B, we'll do this part together. So find S of t for this curve. Give you a couple minutes to do that. I've gone blurry somehow. There we go. Okay. So first finding the tangent vector function, grabbing its magnitude, and again worked out nicely with the Pythagorean identity that reduced to 1, so we should get 2 radical 10 for the tangent function. So then integrating that, it's just a constant, so it becomes a linear function, right? Just 2 radical 10t. How did that process go? Good. Even if you didn't finish, was the approach there? Okay, cool. Excellent. So yeah, we got a linear function. So that's kind of interesting on this helix looking thing, that the arc length is given to us by a linear function. It's like that distance is growing at a constant rate. So that's great. And so now the second part is to reparameterize the curve based on S. So how we do that is we take S. We have this expression that tells us, well, the arc length, how far you've traveled at time t, is given to you by 2 radical 10t. And we just solve this for t to remove it from the equation. All right, so we say, all right, well then t is really the arc length divided by 2 radical 10. So now what we have, that I can have r of t of s, which before, right, let me pull up our previous, because it's way up there. R of t was what? 2t, 3 cos 2t, 3 sine 2t. Cos 2t. And so we're substituting t with s over 2 radical 10. So that's 2 times s over 2 radical 10. 3 sine 2 times s over 2 radical 10. 3 cosine times 2 s over 2 radical 10. And then we get to cancel out some 2's, but that's about it. So my next question is, what is your position after traveling 10 units along the space curve r?
So root 10, 3 sine root 10, 3 cosine root 10.
Right. This is really r of t of 10. Right? Substitute in your arc length, which is traveled 10 units along the curve. And now you know your position. And so t never came up. You know, I mean, we had to do a lot of work to remove it, but it's based on the arc length. Okay, questions so far? All right. So the last idea that I will leave you with is the notion
for that one is the idea that if we're like getting t out of it, we just don't care about how fast it travels or like
right.
how it's getting there, just that this is what it has to do.
Right. This function is based more on just the curve itself instead of any speed with which we can ascribe to t, right, or moving with respect to time. This is really more geometric of a way to represent the function than with some time-based thing, if that makes sense. Cool. All right, last thing here, since this is all connected and curvature is going to come up a lot. So we now have a reference because it's no longer based on t, it's based on arc length. Now we've kind of like moved the axis with which we can pay respect to when we're talking about change, which means and then we can talk about how curvy something is because we're talking about the geometry of the curve itself instead of the speed of the curve, right? The speed of the projectile. So this is kind of a new reference point for us. It's a new characteristic of curves. So let me try to get through the important bits here. Recall that the tangent unit vector is the tangent vector over its own magnitude, right? So that will be important in a moment. But how we define curvature is, right, the deviance or the failure of a curve C to be linear. Right? So if you have a high curvature index, we don't call it that, but if you have a high curvature index, that means you're really bad at being a line, right? And if you have a low curvature index, close to 0, that means you're pretty much a line, right? So it's a measure of how bad something is at being linear. It's another way to think of it is how quickly the curve changes direction. I like this because now we're talking about rates of change, right? And things that we've been playing with already. How quickly the curve changes direction also tells you how curved it is in a certain spot. This really tells us this is the rate of change of our beloved unit tangent vector. And why this and not the tangent vector? Well, because this preserves just the direction, right? And that's all we really care about. How fast is it turning, not how fast is the particle moving along it, right? But how fast is the curve itself changing? So that's the rate of change of the tangent vector. So that's kind of the intuitive explanation. So we use the symbol kappa, which is a funky K, to describe this property. And we say it's the derivative of the tangent vector with respect to arc length. And this is a magnitude. Oops. So this is a scalar. Because it's just a number, it's an index describing how curvy something is. And if you read it as written, knowing Leibniz notation, it's the rate of change of the tangent vector, right? So how fast it's turning with respect to this S is arc length, right? How quickly it's turning. That's what this means. This is one of those places, and this is a cool thing that you might have been exposed to already, depending on what other math and physics you've taken. But that we have different forms for concepts with these equations, and this is a great way to express the idea. It's very concise. It's very simple. It's the magnitude. It's a scalar about how much it's turning, right? How much the direction is shifting with respect to the arc length. This is kind of a bummer to use computationally, right? If you're going to go and calculate something, this is like too general. You'd like a little bit more of a guide. So there are some alternative forms that are nicer, and I'm going to show you those now. But I really want you to use this as the frame for this idea of curvature, how the tangent vector is changing with respect to arc length. So I'm going to draw up some equivalences here. So here, if we use the idea of differentiating both, well, we could do it like that. If we kind of play with the chain rule a little bit here. We can notice that this is really, so let's just say I'm kind of playing with some stuff over here. So if I take that dt ds, remember the chain rule can be written in this way. And this relates now dt ds to dt dt, the parameter for r of t. And so what we can do is actually divide both sides, since this is a number, right? And we can say, well, dt ds is really dt dt over ds dt. So that's nice. So what that means is this magnitude then must be equal to the magnitude of dt dt all over the magnitude of ds dt. We can use one other side fact or nice little corollary, which comes from, where did it come from? Well, it comes from the fundamental theorem of calculus. Yeah. So essentially, since we said that, hopefully I'm not like splitting your attention too much here. But we said s of t is the integral from 0 to t of the magnitude of r prime of u du. If I use the fundamental theorem of calculus on both sides, it means that ds dt is really the magnitude of r prime of t. And I'm going to use that fact because I have ds dt right here. All right, that's the only reason I bring that up. I'm just kind of morphing this thing into something a little bit more nicer to calculate with. So All right, up top I get dt all over. Down here, this is the magnitude of r prime of t. And what's the top? The rate of change of the tangent vector with respect to time. That's really just the magnitude of t prime all over the magnitude of r prime. So this should make some intuitive sense if we're kind of like tracking the notation here. And what is not obvious at all, but I'm going to give to you, and then maybe we'll unpack it next time. That'd be a good place to pick up, actually. Is that, I'll put over here, not obvious. This is equal to the magnitude of r prime cross r double prime all over the magnitude of r prime squared. It's not too bad to go from here to here, but obviously it's not a quick jump. But the reason I give you this is because this is a lot nicer to work with, right? If you're, which you will be practicing problems, finding these things, this is going to be nicer than any of these that it took to get there. But I showed you these because I feel like they still are well connected to that idea of how something fails to be a line and creating an index to measure that. All right, something curving. So there is a notion which is called the radius of curvature, which is really like it's the reciprocal of kappa, and how it's related is essentially it's the radius of the circle that would best fit and just kiss the curve at that point of tangency. Okay, so you can think about if we're measuring how curvy something is. All right, let's say here's my r of t. We're measuring how curvy something is right here. The curvature is some index, and it is measuring, or rather it's related to this radius here. And so this is what we call the radius of curvature, that circle of kind of best fit, quote unquote. And so kappa is 1 over r. It's another way to think about it. And so that makes sense because if you extend this up to, right, what's the curvature of a line, right? Well, how big must the radius be of this circle to like wrap up and just kiss a line? Well, you're going to have to break that circle apart, right, and flatten it out. And it's going to be infinitely wide, right? So the radius of that circle would be infinite, which means that the curvature would be 0 because I'm dividing 1 by infinity, right? So that adds up and that follows. And then likewise, you can think about, you know, what radius would I have to have given a certain curvature, and vice versa. But that's just a nice geometric way to play with it. I'll set us up and I'll have you guys finish this problem on your own. And there's actually an equivalent form to this that I'll give you and we'll use. So a lot of formulas. You can plug these into your formula sheet on the test. Another way to write this. And if you can't wait to see a proof, it's on page 905. This is a little bit nicer to compute. All right, so let's keep it simple. I've got this function, and if you think about the shape this thing is, it's a parabola in the zx plane, right? XZ plane, and it's really right along the x-axis. All right, am I saying that right? It's taking in z and along the xz plane. Yeah. So anyway, it's a parabola. So to find the curvature of this simple parabola in R3, we would use the formula that I just gave you, would be best, which is what? R prime cross R double prime all over this guy cubed. So you'll need to take a cross product up here, and you'll need just really the first and second derivatives, or the tangent vector and the second derivative of r to compute this. So set yourself up with these two, and then you'll need to compute the cross product. Which, remember, does the order matter in the cross product or no?
Yes.
It matter?
It definitely matters. Definitely matters. So compute the cross product here, and then you've already got the tangent vector, so you're going to need the magnitude down here. And so I can leave you to that. So I'll say left to the pros. This is why we pay you guys the big bucks here. Okay? No, really, I'm trying to be respectful of your time and in a timely way. But I'll post the solution to that with the class notes right after class. I'll give you the CalcPlot 3D link to play with. Did I leave anything else untied? Any questions top of mind right now? Awesome. Getting into some fun stuff here. I'm digging it. So, and it's like I'm really impressed by your guys' focus. I mean, I know this is it's later in the day, but I see you're all tapped in the whole class, and I want you to know it's observed, it's noticed, and it's appreciated. And keep it up. So, all right. If that's it, I'll let you guys go. We'll see you next time. Take care.
I have one question for you, if you don't mind.